So this is Bitophysics number 65, I believe. Is that right? Yeah, 65, the fifth in our quantum mechanics series. I'm John Mallinckrodt, your host for Bitophysics, and if you open up the slides there at the top of the page, you'll see links to all the bites of physics, a few nibbles of physics that I've done, and finally just a link to all the public documents that I create every once in a while when something moves me to write a 1 or 2 or 3 page treatise on this or that. So you can explore those things if you want. We have been talking about quantum mechanics, the Schrodinger equation. We started talking about solutions of the time-independent Schrodinger equation, and then we put other wave functions that we got in motion, saw how we could create arbitrary wave functions out of combinations of so-called energy eigenfunctions. And then we put them in motion using the full Schrodinger equation, sometimes called the time-dependent Schrodinger equation, but it's just the Schrodinger equation, which tells how wave functions evolve with time. So on slide 2, the first content full slide in the presentation. As usual, just a quick takeaway from part 4 of this. And one of the things we talked about the most was the trade-off between the knowledge of position and of momentum/energy via kind of the Heisenberg uncertainty principle. And associated with that are these ideas of group velocity, which is loosely the speed of the envelope of a wave packet. It's the speed with which kind of the region in which a particle is likely to be found moves. So that's really the envelope of the wave packet. That envelope of the wave packet translates pretty directly into the region in which the particle represented by the wave function is most likely to be found. And so it's better sometimes simply to look at the so-called probability density that you get by taking the square modulus, as it's called, of the wave function itself, as shown in the diagram there at the bottom. That black line at the bottom shows you where the particle is most likely to be found. And that diagram shows a wave packet moving in from the left and largely reflecting off of a barrier. Because it's a fairly localized wave packet, it consists of a combination, a continuous combination of energies above and below the height of the barrier, some of which can continue traveling to the left or to the right, even past the barrier, but some of which get reflected off of the barrier, creating these standing waves. I didn't talk about phase. First of all, phase velocity is kind of loosely the speed of a peak in the wave function itself. So if you look at the red and blue real and imaginary parts of the wave function, as we've been talking about them, those peaks roughly move at what's called the phase velocity, the velocity of the wave. And doesn't necessarily match the group velocity. In fact, sometimes they're in opposite directions, as we may notice today as well. And when waves reflect off of something, then you get these kind of standing wave features, as you see in here, especially in the probability density at the bottom. Those funny little waves in the envelope are the result of interference between a wave that's now moving to the left, having reflected off the barrier, and waves that are still moving to the right. And we put those things in motion, did a lot of that. If you want to, you can go back and review part 4 to see movies of those things. So that's kind of a quick review of some of the things we did in part 4. What I want to do today is start with 3 movies that show just one particular kind of a situation, which is going to be related to to alpha decay, the nuclear decay process called alpha decay, in which a radioactive isotope emits an alpha particle, which we'll see is a helium nucleus. And so to this end, what I've done is I've taken a scenario which is actually supposed to be a double a double barrier or a double well from this software. Oh, that I linked to on, by the way, yeah, on slide 2, I have a link to the software that I use to make these videos. It's very general, so I can kind of move walls around. I can move them up and down. I can move them back and forth with all those little adjustment parameters that you see there. But what I've created here is I've created a potential well beyond which is just an open region. So there's a region in which wave functions, or which a particle could be trapped if you want. And then there's a region on the other side of that narrow barrier in the middle, beyond which there's apparently, as far as you can see, there's no barriers beyond that. So a classical particle in that region could move to the right forever because there's nothing to impede it. But there is a potential well that is separated from that open-ended region by the barrier on the narrow barrier, and also a barrier that, as far as we can tell, extends infinitely to the left. So we would expect, from what we now know about about quantum wave functions, that the wave function might feel a little way into that barrier on the left, but it would quickly find out that there's no place for it to go to. So it would be really literally hard trapped by that barrier. Whereas on the right, that narrow barrier on the right of the well is narrow. The wave function will extend into it in a way that we've come to hopefully get a little intuition for. Depends on how high the barrier is and how wide it is, but it'll extend into it a little way, and it may feel its way out into that, once again, classically allowed region. And of course, this is tunneling. We've already really seen tunneling in this form, but we're going to talk about it a little more quantitatively when we talk about alpha particle decay at the end of this thing. So if you put this video in motion, what you'll notice, so first of all, before you put it in motion, what I've done is I've created a fairly unlocalized wave packet. This is a pretty broad wave packet. And I did that on purpose because I wanted it to be made of a very narrow range of energies. You can see in the green in the top panel there, that's kind of the range of energies that I needed to use to create this wave packet. And those energies are quantized within the well, because I can't have any energy. Well, I shouldn't say that. Never mind even what I said. It doesn't even matter. It's made of a narrow range of energies. There is some quantization going on, but let's not worry about that. If you set this thing in motion, you'll notice that the wave packet right at the beginning is already in the free region. So it's just going to travel off. And there's going to be a region, there's going to be a period of time in which things kind of settle down. But if you start that video, you'll see a big chunk of probability moving off to the right and then out of the screen entirely, leaving pretty much a trapped and oscillating wave function in the well. And it really is pretty trapped. I think you'll agree. It's not able to feel its way out. If you see kind of the exponential decay of the wave function within the barrier, by the time it's halfway through the barrier, it's kind of given up. There's really nothing that makes it to the far side of that barrier. It oscillates in a kind of hard to predict way, because it's a sum of different energy wave functions, different energy eigenfunctions, which are all interfering with each other, producing standing waves with themselves and with other waves. And so it's all kind of complicated. But the important thing is that after some very small amount of time, all of the probability is pretty much confined to that well. It doesn't leak out primarily because the barrier is so high that the wave function has to die out quickly. We learned in the first one or two of these that when the barrier height is tall, the wave function dies out quickly. In fact, when it's infinitely tall, the wave function can't extend into the forbidden region at all. It has to go literally to zero right at the edge. But when it's not infinitely tall, it extends in a little bit, and more as the barrier gets smaller and smaller. So if you go to slide 4, on slide 4, what I've done is I've taken the barrier and I've made it much lower, but also much wider. So now the barrier isn't much taller than the energies that this particle, that this wave packet is constructed from. It's still taller, so it should trap them. But it's not much taller, and so you would expect the wave function now to be able to reach very far into that forbidden region. And now the only question is, can it reach far enough to get all the way through that now quite wide forbidden region? So once again, you can just hit play, and you'll see once again a period of time during which some stuff gets through and travels off. You see it traveling off to the right, but pretty quickly it starts to settle down. Very little travels off to the left. There's still off to the right. There is still some, but you do notice also that the wave function dies out very slowly now in the forbidden region. And the probability that remains in the well kind of sloshes back and forth. If you kind of watch it, you'll see that the probability kind of sloshes over to the right, and then it sloshes over to the left, just as if this were a particle bouncing back and forth in that well. And that's indeed what it really does represent, is the most likely thing is a particle kind of sloshing back and forth with the speed that you would expect for a particle of the basic energy that it has. And when it hits that wall on the right, the probability extends way into that wall. But it's a very wide wall, so it doesn't really matter. After a while, after some probability has kind of leaked out from the original wave function, you're left with pretty much just a trapped wave, a trapped particle that's sloshing back and forth in this probabilistic way. So let me stop there for a moment, ask for if there's any questions or comments on slides 3 and 4.
I have a question. Mm-hmm. So as we let this particle go from left to right in both cases, we're observing that, of course, in the second case, because the barrier is lower, the probability of finding the particle, outside or in the forbidden region is greater, which is what we expect. But Why does it die out after a while? Like, you would expect that these probabilities that are outside in the forbidden region, they keep existing. Like, why would they die out?
Right.
Why is the particle now confined in the region that it wasn't confined in the beginning?
Yeah, good. Of course, it wasn't confined in the beginning. Actually, unfortunately, I was kind of constrained by this software. It will only produce wave packets or traveling waves, and I with the particular function that I drew there, I couldn't use a traveling wave. I had to use a wave packet, and had I used a very localized wave packet, it would have been constructed from a large variety of energies, which I didn't want. So I would have preferred to just be able to draw my wave function at the beginning, but it doesn't allow me to do that. So there is that transient phase during which things kind of settle into more like what I wanted to have happening. But let me address your first question, which is the most important thing, and just draw your attention back to what we talked about in the first one or two segments. In a forbidden region, the wave function must curve away from zero, right? And so it can do that in two ways. And it turns out actually the mathematical solution for the wave function is either a decaying exponential or a growing exponential. It's more than just that it must curve away or toward. It literally, in a case like this, be a combination of a decaying exponential and a growing exponential. If there's any growing exponential, when I say growing, I mean in this case, as we move to the right. If there's any growing exponential, then the wave function on the right side will just get bigger and bigger and bigger and bigger, even though the region is still forbidden. I could extend that forbidden region out to infinity, and the wave function would grow and grow and grow and grow. So if that barrier does go out to infinity, there can't be any growing exponential, because that would mean it gets more and more and more likely to find it in a place where it can't be. And we don't want that kind of thing happening. So we must, and in fact, it's not just that we don't want it, it's that mathematically you end up finding that the only solutions that work in the forbidden region are decaying exponentials. And so it will curve away from zero, but always approach zero and never grow, because if it ever started growing, it would have to continue growing. Does that make any sense?
Yes, but I do have a follow-up question.
Okay.
In that case, what is the real difference between case 1 and case 2? So is it that when I do summation of the absolute value of phi x, the whole thing squared, if I do this summation, will it be less or more in the second case?
In the well itself, you're saying?
Yeah, because they both, if you leave the system, over time, they will both produce the same shape. It will be dying out because of what you said, so it will always tend towards zero. And so what's the real difference between the two cases?
Right. So the because I didn't do any fancy calculations, I don't know. I think it's probably the case that in the first. Well, I really don't know. I don't know which one leaves you. But if we could think of it this way. I can think of the original wave function as representing. This will be useful for later. Suppose it represents Avogadro's number of particles, not just one particle, but Avogadro's number, because that's really the way we do quantum mechanics experiments. In a sense, we do them statistically. We do them on either one particle many times, or just a lot of particles. So you can think of that wave function as representing Avogadro's number of particles, some ungodly number. And then the ratio of the total energy under that probability curve at the beginning, or sorry, maybe I should say at the end, to the area at the beginning, just tells you how many are still in the well at the end. It's going to be, if you take the total area under that curve at the end, it's going to be less than it was at the beginning, because some of it escaped away. And that is a probability curve. So the area under the curve from negative infinity to positive infinity is constant. It's just that some of it has escaped off to the right. So I don't know how much ends up, and that's going to depend on the details of the initial wave packet, my design of the barrier, etc. I'm not sure that answered your question, but did that help?
It most certainly did. Thank you, sir.
Okay, good. So now in slide 5, what I want to do is I want to make the barrier, high, but not terribly high. I don't really care too much. Mostly what I want to do is I want to make it narrow, but I want to make it some combination. Notice it's both the width. What I really established in slides 3 and 4 is it's both the height and the width that end up trapping things. If I make it high enough, I can make it as narrow as I want and still trap things. But now I'm making it kind of high, but also kind of wide, right? But basically, it's pretty narrow. It's going to be pretty easy for the wave function to get through that, because it's not going to be damped down very quickly by the height of the barrier, and the barrier itself isn't very wide. That may be in some ways the most important part of it. So now if you look at what happens, you'll notice same kind of behavior as before. Stuff moves off immediately. The junk I didn't want anyway moves off immediately to the right. And you're left with a particle kind of sloshing back and forth. The probability is wavy and standy wavy and all that, but it's sloshing back and forth. You can kind of see that. And every time it sloshes over to that narrow, not very high barrier on the right, a little more of it gets through, right? Each time that happens, there's a little chunk of probability that moves off to the right. And I'm going to let this one goes 3 times as long as either of the first two. And you might think at some point, it looks kind of trapped. Yeah, but you'll notice it really never gets to the point where there isn't some probability leaking off to the right every time some probability butts up against that wall, right? The particle that's being represented kind of comes over and hits it. You'll see every time that sloshing particle comes over, a little bit leaks out and goes over to the right. Now, it's not going to go long enough for you to see this, but I want you to appreciate the fact that in this case, it's not going to be very long before there's just not much probability at all left within the well, because it just keeps leaking out. No matter how small it gets, some fraction of it, and that's the important thing too, the smaller the remaining probability gets, the smaller the probability that leaks out is. But that amount of probability that leaks out each time is kind of a fixed, or at least a semi-fixed fraction of the probability that remains. If there's not much probability remaining, then the wave function itself won't be very big when it hits that little wall. But some fraction of it will get through. And that's kind of modeling the idea of a half-life. The smaller the amount of probability left, the smaller the stuff that leaks out will be. But the fraction per unit time remains relatively constant. I don't want to say constant because this is way too complicated a wave function to say that about. But you get that kind of behavior as well as I can model it using this software. So let me stop there for a moment. Let's just see if there's any comments.
So are we talking about if you leave the system run for a long time, are we suggesting that in your analogy of taking the Avogadro's number of particles, at some point, at infinity, all of those particles will escape, all of them will decay if you stay there? Or will it reach a certain limit where, okay, there's 50% of them, let's say, they will continue to exist here?
Yeah, that's right. That's a really good question, and the answer is no. And that's why I was talking about kind of that given fraction escaping. If you were to look at that over like 10-second or whatever, over relatively large, let's say over 3 or 4 slosh intervals, if you look at the total probability at some time in the well, and then you look at it 3 or 4 sloshes later, whatever that period is. Maybe it's down to 97% of what it was at the beginning. Maybe the remaining probability in there is 97% because 3% is leaked out. Then kind of over the long term, what you'll find is that's a constant. Every time you wait like 3 sloshes, you're going to lose 3% of whatever remains. 3 more sloshes, use 3% of whatever remains. 3 more sloshes, 3% of whatever remains. Now does that eventually get to 0? No, not if you're talking about mathematically, but yes, if you're talking about Avogadro's number of particles, because at some point it's going to get down to 1 particle, and that 1 particle is going to slosh back and forth, probably not going out this time, probably not going out next time, probably not going out the time after that. But after about 30 times, with a 3% probability every time, it's probably gone. And then you got no particles left. So, yeah, that's kind of the way half-lives work. When you've got Avogadro's number, you can just say, okay, half remain, half remain, half remain. You try to do that mathematically, you never get to 0, but you have to remember that you are talking about discrete, a definite integer number of particles in that case. Good?
Yeah, perfect. So we can say that a thin enough barrier will always leak. And so at the end of the day, this is not a container anymore, because if you leave it for a long period of time, it's not containing stuff really.
That's right. And I want to be really clear, none of these were leak-proof containers, right? I kind of drew an artificial distinction. Those first 2 containers leaked. And if you waited long enough, there'd be nothing left in them. But they leak at a dramatically lower rate than the last one. So I think that's really important to see too. Really, these things have to leak because the wave function doesn't go to zero by the time it's at the other end. So it will leak if you have an energy that is an energy that can exist on the outside, then it will leak, and that's going to be kind of important when we get to alpha particle decay too. If you have a nucleus that can alpha decay, it will. It doesn't matter what the energy of that alpha particle is or anything else. I'm getting a little bit ahead of myself. Okay, so let's go on to slide 6. The next three slides, maybe, just want to kind of review some things. We'll get back to the main thing in a minute. But I think it's important, especially for people who may not kind of remember all their high school physics. Let's just go through a few things we know about the atom and the nucleus, et cetera. The figure on page 6 shows kind of the history of the idea of the atom. And then kind of the most important figure in there is probably the one in the middle, the Rutherford atom. Dalton, chemist Dalton, basically kind of established that matter's made of atoms. The model of the atom that he had was little balls. Right? There was nothing to distinguish them other than there had to be something that distinguished them, but he didn't have any reason to suggest any structure to the atom other than the fact that there are clearly different kinds of atoms. The mental model at that time would have just been basically balls, maybe different color balls, maybe balls with dimples on the sides. Who knows? But balls. And then at some point, it became understood that atoms were made of charged particles, that there were electrons, for instance, and the electrons were parts of atoms. And so the idea became this, what's sometimes called the plum pudding model, that this atom was just kind of an amorphous blob of positive stuff with little plums stuck in them in the form of electrons. And there was a lot of work done to try to understand atomic spectra from the idea that these electrons would arrange themselves in that blob to be as far apart from each other as possible, and then would have little oscillation frequencies around those stable positions. People tried to actually work out the spectra of different atoms by figuring out what those oscillation frequencies would be and thinking they'd be little antenna for radiating electromagnetic radiation. And that went basically nowhere, but it seemed like a promising direction to go. And then the most important thing was in 1911 when Rutherford shot alpha particles, the things we're talking about, things he didn't really, I think Rutherford still didn't know what an alpha particle was. He knew it was a positively charged particle that was very energetic. And at this point, we knew that there were so-called radioactive isotopes that emitted various kinds of radiation, which we'll get to in a minute, including alpha particles. And he shot these alpha particles at thin foils of gold and found, much to his surprise, that almost all of them just went straight through the gold foil as if it was nothing. They didn't slow down. They didn't deflect. They just went straight through the gold foil. But every once in a very long while, one of these alpha particles would come straight back at him. Like it had hit something really big and massive. Right, so you got all these alpha particles just penetrating this gold foil with glee. Every once in a while, one comes straight back at him. And frankly, every once in a while, one would deflect at 10 degrees or 30 degrees or something from its trajectory. But most of them just went straight through. And the implication was that matter must be made basically of nothing, with little, very massive, hard nuggets embedded. And the idea became that an atom might be this model where we have a nucleus, a positively charged nucleus, very dense, very small, surrounded with electrons. So the size of the atom is determined by this electron swarm around the nucleus, but all of the mass of the atom, basically, all of the mass, was in that nucleus, which you very rarely hit when he was shooting the alpha particles. And with the dawn of the quantum theory, about the same time, there was the so-called Bohr model, which was the first one that succeeded in explaining very precisely the atomic spectrum of hydrogen. And it came from just postulating that electrons orbiting a proton could only orbit with integer multiples of Planck's constant as their angular momentum, which was kind of a bizarre thing to postulate. But if you did that, you got the spectrum of hydrogen basically exactly until you looked at it in so-called fine structure. So the Bohr atom put these electrons into very specific quantized orbits. And after Schrödinger in 1926 with the wave equation, we now understand the electrons to be wave functions of particles that are bound to the nucleus in a three-dimensional potential well. The shapes of the so-called electron orbitals are just the energy eigenfunctions of an electron wave bound to a very massive nucleus by this attractive inverse R squared electrostatic attraction that they have. So all these one-dimensional things that we've been talking about, one-dimensional potential wells, have kind of obvious analogs in 2 dimensions and then even in 3 dimensions. This three-dimensional potential well means that the electrons are free to move in 3 dimensions, but they're bound kind of radially to the nucleus, and then they have these energy eigenfunctions, which are waves in the region of that nucleus. Okay, so that's kind of a hopefully just a little review. I'll pause briefly to see if there's any questions, but that's kind of the history of atoms in a nutshell. Now I want to dive into the nucleus itself. So the nucleus, we now know, consists of a collection of protons and neutrons. The neutron itself wasn't discovered until after quantum mechanics made its debut. We didn't know that the nuclei of atoms had neutrons in them. It was discovered, I think, in 1930. But we now know that nuclei are made of protons and electrons. The number of protons tells us the chemical element. The number of neutrons tells us the isotope of that element. So we can have helium-4 is the most typical isotope of helium. It has 2 neutrons and 2 protons. But there's also helium-3, which has 1 neutron and 2 protons. I think there's helium-5, although I don't know. There's not very many options there. Uranium, we've got U-232, 235, 236, 238, all sorts of isotopes of uranium, all of which have 92 protons and all of which have something like 140 some odd neutrons. These nuclei have decay modes that gave out energetic particles that we didn't know the identity of at first, and so they were given names alpha particles, beta particles, and gamma particles. We now know that an alpha particle is a helium nucleus. It's 2 protons and 2 neutrons, which happen to be a very tightly bound system of nucleons. And we also know that beta decay is an electron, an electron or a positron, an anti-electron. In a beta decay, a nucleus emits an electron or proton that is associated with the conversion of a neutron to a proton or a proton to a neutron. This is called the nuclear weak force. I'm not going to spend any time. We're not going to talk about that. We're talking about alpha decay here, but I'll just briefly set the stage because we are going to mention these a couple more times as we see things about the potential well. So in beta decay, a proton or a neutron turns into a neutron or a proton and emits an electron or a positron, a high energy electron or positron, which is called a beta particle, which was called a beta particle before we knew what they were. Gamma decay is an isotope, is when a nuclear, an excited nuclear isotope emits a high energy photon. We now know that a gamma particle is simply a very high energy photon, higher energy than an X-ray photon, which is also a photon. Gamma decays, or a gamma photon is about 1 million times as energetic as a visible photon, and about 1,000 times as energetic as an X-ray photon. Although those are all very, very touchy-feely kinds of numbers. You can differ by factors of 10 or 100 and not be wrong. There's also a kind of a decay called fission, where some nuclei just break apart. They just break into two fairly large or multiple multiple nuclei of lower atomic number isotopes. But I don't want to talk about that really either. We want to talk about alpha decay, this emission of an alpha particle, because that's the one that does involve tunneling. The others don't, as we're going to see on the next slide. But let me stop there for a second. Any comments or questions? Anything going on in the chat? Let's see. Well, let's see. I've got Kirko. What's Kirko saying? So if you were to put, I got to open up my chat. If you were to put in my own words, the more time at energy barrier above the standing wave, the higher amount of energy goes through the barrier. Okay, I think maybe that was from some time, a little time ago.
Yeah, we were talking about the waves staying inside the barrier,
Right.
and some of them escaping or decaying.
Right, and you don't want to think of it as energy escaping. You want to think of it as probability escaping, because it's really the more probability you have on the outside of that barrier, the more likely it is that you will find, that one particle or the more probable it'll be that you'll find that one particle that you started with, or the larger number of whatever total number you started with, you're going to find outside that barrier. So it really is, you don't want to think of it as energy escaping, it's probability escaping. And the net probability tells you where you're most likely to find things, inside or outside, is really all we're concerned with here. Okay, so let's move on to slide 8. So let's go through this pretty carefully here. How do you make an atomic nucleus? You have these protons which have positive charge equal to the charge on an electron. Electron has a negative charge. Protons have the same exact charge, as far as we know. Every indication that is exactly the same amount of charge, but it's positive rather than negative. Those appellations are arbitrary, but same amount of charge, just the opposite charge. Protons powerfully repel each other. When you get them as close as they have to be in a nucleus, they are really close. I think one thing I didn't point out in the previous slide is that the nucleus of the atom is about 100,000 times smaller than the atom itself. That's largely what Rutherford kind of inferred that from how unlikely it was that alpha particles were reflected back at him from gold nuclei. Nucleus of an atom is about 100,000 times smaller than the atom itself, a tiny little core there. And when you get two protons that close, within a 10 to the minus 15th meters of each other, 1 femtometer, they are really strongly repelling each other electrostatically. And yet, somehow in the nucleus of an atom, they stick together. And so we invent originally, and then we do experiments, and we now know more and more about where this force comes from. But we invent a thing called, appropriately enough, the nuclear strong force. And that strong force has a weird behavior because it doesn't act between protons at all until they're right next to each other. When they're right next to each other, it acts, and it acts powerfully. But if you separate them by 10 or 15 femtometers, there's no force at all. So it's a short range, very strong force. And it's nice to kind of compare that to the difference between magnetic forces and touch forces. When you have a couple magnets, you bring them close together, you can feel the force getting stronger and stronger and stronger. Right? That's a long-range force. But contact forces are kind of like the strong force. They don't act at all until things are right next to each other. That's the kind of the way they feel. Now we know, in fact, that contact forces really are just electrostatic forces between electrons in the outer orbitals of the atoms, on the surface of your finger and the surface of whatever it is you're touching. But contact forces act, for reasons we won't go into here, like short-range, powerful forces. So this nuclear force is very much like that, with the exception of, usually we think of contact forces as always being pushes, and this force is a pull, right? This is an attractive force that only acts when things are right next to each other, touching if you want. Although touching is also always a weird thing to talk about when the particles you're talking about are represented by waves and not hard balls. But at any rate, it has the effect of kind of a touching force. That strong force is felt by neutrons and protons. And so when you put neutrons into a nucleus, the nice thing about doing that is that it adds a lot of strong force glue without the downside of adding any electrostatic repulsion. So neutrons will also attract each other. If you put a neutron right next to another neutron, it'll attract very powerfully. But if you pull them apart, they'll be perfectly happy to be apart, but they won't repel. They'll just be apart. Whereas protons touching each other, there's going to be a very powerful attraction, but as soon as you pull them apart, they will now repel and move energetically apart. Interestingly enough, I don't know the reason for this. Maybe somebody does. I was just thinking about it as I'm talking. I don't believe you can stick a proton to another proton. You need at least a neutron in there to provide enough nuclear glue, strong force glue, to hold the two protons together. Let's see, what else did I say here? Right. So the potential energy functions, the wells that these protons and neutrons find themselves in, are a little different. There's two figures on slide 8. The one on the left shows this potential well in a symmetric fashion. So let's deal with that first. It's we're looking at a little slice across this potential well. And you'll notice that the proton, the potential well in black, is the one for protons. At some distance from the nucleus, there's a repulsive force. Whenever we learned in the first episode of this series that when you have a decreasing, so that potential, if you look at the potential, the black potential on the far right, it's decreasing with distance, which means that if you put a particle in that region, it would feel a force to the right where its energy would get more and more, would exceed by a larger and larger amount the potential function. And that means that as it moves to the right, it's going to move faster and faster and faster. It does that because there's a force acting on it to the right. A decreasing potential like that means that the force is to the right. Whereas if you look on the other side where the potential is decreasing to the left, that's a force to the left. And it's just drawn this way to kind of show you a little slice across this potential well. But the potential gets higher and higher because of the electrostatic repulsion until the objects get close enough that they're in contact, if you want, where the strong force comes into play and creates this deep well, an attractive force that keeps things in there. Whenever they move apart, they experience this force back toward the center of that well, and that's what keeps the nucleus together. In the case of the protons, that well is raised a little bit because of the electrostatic repulsion that they have. The neutrons feel essentially the same well, but because they don't have the electrostatic repulsion, it's just a well that goes immediately to zero outside. There's no repulsive force when you get outside that well. So that's what's shown on the left, in the diagram on the left. And let me just stop for a moment before going to the one on the right, because there might be questions. There probably are questions about that. Feel free. And once again, invite anybody on stage if you want. If you have questions, probably best to come on stage because I just don't pay much attention to the chat. Although, my friends who I haven't made moderators yet, let me do that too, are always good about kind of paying attention to that. Okay, no questions? Let's move over to the diagram on the right, which I took from another place. It shows the same thing, but now rather than kind of showing the two wells superimposed, it just shows the proton well. It shows half of the proton well over on the right and half of the neutron well over on the left. And this makes a really nice point in that what do we have within this well? Well, we have quantized energy levels. We have a particle being represented by a wave, and for energies less than the energy that a particle would have to be a free particle, those energies have to be quantized by the boundary conditions on the wave function. That lowest one will be kind of a no zero crossing wave function. The second one will be a 1-0 wave crossing wave function, et cetera. That's not really quite true because this isn't really one-dimensional potential wells anymore. But effectively, it's the same kind of thing we saw before. And so you see all the blue lines representing energy levels. And just a fact that we won't dwell on here either, it turns out that when you talk about situations like this and you start putting neutrons and protons into those energy levels, there's a thing called the Pauli exclusion principle, which was just a principle to begin with, and it applied to electrons when it was first discovered, which basically it just said that in atoms, these quantum functions, these eigenfunctions that you find, can only have two electrons in each one. You can have one spin up electron, it turned out, and you can have one spin down electron, but you can't put two particles into a given wave function, into a given quantum state, is what we really say. In the case of electrons, having different spin makes the state different. So you can put two electrons into the same energy eigenfunction if you make the spin part of their wave function different, and then electrons can only have spin up and spin down, so that means two electrons in each one. Just a second, Shamash, and I'll get to you. This Pauli exclusion principle we now know is a quantum feature of what we call fermions, particles that have half integer spin. There are particles that have whole integer spin that don't obey it. I'm just telling you a bunch of stuff now, by the way. This is not something, there won't be a test on this. I'm not explaining to you why. But I wanted to give you this because I'm going somewhere with it. The Pauli exclusion principle, basically we now understand to say you can only put one fermion into each allowed quantum state. That's really the full expression. And it's different for so-called bosons, particles that have integer spin. And those are the only possibilities, half integer spin and integer spin. Protons and neutrons are fermions, and so they obey this principle. And we'll get to that in a second after I take Shamash's question. Oh, Shamash. Oh, yeah, there you are. You are there. I was looking for Shamash, and I saw only Logic Guy.
No, I just got excited because I wanted to wait until the end to ask about the Pauli exclusion. So yeah, we can. I mean, if you feel like dwelling more on it, or even at the end, but we can take Kirko's question first, and there's a question in chat from the Method as well.
Okay, good. I don't want to go into the Pauli exclusion principle very much here. I think I've said almost enough. I will use it to say one more thing when I get back to it. But it's very interesting. It has really no relevance to the central thing we're talking about. But I wanted to make one little point while we're here. Go ahead, Kirko.
I just real quick before you continue. One thing I'm not really getting right is if we look at the current I guess more accepted model for the atom is Schrodinger, so it's just probability of where these electrons are. I don't understand how the Pauli exclusion principle still is a thing, because it's not as if it'd make more sense if you can say there's two electrons here, there's two electrons here, and they have to be one spin up, one spin down, one spin up, one spin down. But there's no actual location of these electrons from Schrodinger.
Yeah, that's right. That's right. No, as we understand, the Pauli exclusion principle really was kind of originally mysterious. It was just something that was invoked to explain why in atoms you didn't have all the electrons in the lowest energy state. Why is that? Well, okay, they can't. You can put two in there, one spin up, one spin down. And it became better and better understood. We now understand that it's just a special case. That particular thing is just a special case of the more general statement that fermions, particles that have half integer spins, can each energy state can only be occupied by one fermion. You can only have one fermion per quantum state. And the quantum state is, everything. If the spin is different, then it's a different quantum state. If the energy level is different, it's a different quantum state. If the angular momentum is different, it's a different quantum state. We say basically we specify the state in the case of atoms, bound particles, by quantum numbers. And there's 4 quantum numbers that represent the states of an electron, only one electron per state. And that means 2 per energy state, because of the fact that the spin is not part of the energy function. Actually, I didn't even say that right. Anyways, I say we can talk more about Pauli exclusion principle maybe at the end. I don't want to get bogged down on it here. And was there a question in the chat too? How does the nuclear force work to overcome the electrostatic repulsion? Okay, good. Yeah. So I'm not going to. That's a really important question, and we now understand it a lot better than we do. I'll say only this about it. We now understand that the proton and the neutron are not fundamental particles, that they are, at least within the standard model, they're better understood as being composite particles. A proton is a combination of 2 up quarks, each of which has a charge of 2/3 the elementary charge. I should say, 2/3, positive 2/3 of the elementary charge, and 1 down quark, which has a charge of negative 1/3 of the elementary charge. So you put those 3 particles together, 2 up quarks, that gives you 4/3 of a charge. 1 down quark gives you negative 1/3. You end up with 1 positive charge. And the strong force we also understand to be actually not operating between neutrons and protons, but between quarks. So what's really going on is the strong force is the thing that binds quarks together, and it kind of leaks out when you have, and you can kind of understand this a little better now that if you think about the touch analogy. When you touch something, you're really putting it's short range electrostatic repulsion from the fact that atoms, the electrons in the outer shells of the atoms in your fingers, are being strongly attracted to the nucleus, and so there's a lot of electric stuff going on there. But when you put something else right next to your finger, a little bit of that electric force leaks out and forms this short-range, strong repulsion force that you don't notice at all when you're further away. So that's maybe a slightly better way of thinking about the strong force. It's a thing which is acting between gluons, and then it kind of leaks out between the things that gluons make up, protons and neutrons. And yes, and gluons is the name we give for the thing that causes the strong force. Just like photons turn out to be the name for the thing that causes the electrostatic force. When the exchange particle is the language that we use. But now I'm getting kind of far afield again. There's so much to talk about here, and it's also, once again, as I've said many times, it's not my strong point area. I know enough to be dangerous, but then that means enough to be probably fantastically wrong if I get pulled too far afield. So let's get back to the story here. I want to look at the diagram on the right on page 8.
On page 8. So what are we seeing with these blue lines, the horizontal ones, and why do we have this black line in the middle right there? Yeah.
Exactly. Good question. So I already said that the neutron potential well is lower than the proton. The proton's kind of raised up by all this repulsion. The protons don't really want to be there because of the repulsion. The neutrons have no repulsion, so they want to be there more than the protons do. Their energy well is deeper, but it's the same kind of size, and we already know that you get these quantized energy levels. And you notice that neutrons, the lowest energy neutrons, can be lower energy than the lowest energy protons. So we want to make a nucleus, we put some protons in there, we're immediately going to want some neutrons. And maybe this is the answer to my own question. The time you put your first proton in there, you're going to want neutrons. Let me actually deal with the black line first. So we fill up these things. They're fermions, and so they obey the Pauli exclusion principle. You can only put one in each energy. You can put two in each energy state, a spin up and a spin down. It's just like electrons around an atom as far as that goes. And we fill these energy levels up. And we fill them up to pretty much, there's other things that go on here, but they get filled up pretty much to the same energy level. And notice a couple things about that. That means there's going to generally be more neutrons in a nucleus than protons, because when we fill them up to the same energy level, there's more neutron energy levels below that than there are protons because of the depth of the well. And that's exactly what we see. Heavier isotopes always have more neutrons than they do protons. So we see that. Number two, what would happen if I had a nucleus that had, say, too few neutrons, had more had protons up to a higher energy level than they had neutrons? So suppose I had like 2 or 3 protons above the energy of the highest energy neutron. Well, here's what happens. One of those protons says, hey, I could make us lower energy if I turned into a neutron. Basically, this is what happens. The proton's sitting there at a high energy level. It's seeing that if it were a neutron, it could fit into a lower energy, unoccupied neutron energy level. And so it does. It turns into a neutron. And in the process, it emits a so-called positron. That's beta decay. So beta decay is the result of a nucleus trying to balance out this thing, trying to get this so-called Fermi level thing to work, trying to balance out. If I have more neutrons than I have protons, I have some neutrons that are at higher energy levels than vacant proton states. A neutron says, "Hey, I could be at a lower energy if I turned into a proton," and so it does. And in the process of turning into a proton, it emits an electron, and that electron is a so-called beta particle. Both of those things are beta particles, but there's beta plus and beta minus particles. This is beta decay. Beta decay is the result of trying to balance that out, and it's mediated by the so-called weak nuclear force. Whatever that means. I've never actually been able to wrap my mind around that being a force, but that's the language we use. So that's the thing I wanted to say. The reason I wanted to kind of do the Pauli exclusion principle and show these wells is kind of to understand that why nuclei have more neutrons than protons, where beta decay comes from. And finally, one more thing to say. Sometimes you have a nucleus which just has a proton at a high, or a proton or a neutron, doesn't matter, in a high energy state, and there's a lower energy state below it. This is what we call an excited state. A proton is in there's an empty proton energy level below the energy of a level that's actually occupied by a proton. And the proton just says, "Hey, I can be lower energy if I just go into that state." But in the process of going into that state, it has to get rid of that excess energy. And that excess energy is emitted in the form of a photon. And because the kinds of energy differences that you see are typically measured in millions of electron volts, that's the energy of these gamma ray photons that are emitted when an excited state of a nucleus decays back to its ground state. And this is entirely analogous to the spectrum of atoms. An atom has the visible spectrum that it does because the energy states of electrons orbiting the nucleus are usually measured in not millions of electron volts, but just electron volts, 1,000,000 times less than what you see in the nucleus. And if you have an electron in an excited state, that electron can drop down into a lower state, maybe the ground state, and in the process emit a photon with an energy not of 1,000,000 electron volts, but an electron volt. And that puts it squarely in the kind of visible range, visible-ish range of the electromagnetic spectrum. So that's an entirely analogous thing. So you see all sorts of great things happening here. I've kind of explained beta decay to you. That's the balancing of the number of neutrons, protons. I've explained why there's more neutrons in the nucleus than there are protons because of the depth of the neutron well compared to the proton. And I've explained gamma decay in terms of just an excited state of a nucleus decaying back to its ground state. The one thing we haven't actually explained, well, we haven't explained fission either. I'm not going to do that at all. But the one thing we haven't really explained in terms of decay is alpha decay, which is what we came here to do 5 weeks ago, and we're going to finish up next. So let me stop there for a moment.
So very quickly, maybe I'm going into too much detail than you actually want here. Just let me know. So we have this massive nucleus, right? And you have all these neutrons, and it's just too much, or all these protons, and it's too much. So one of them will decay. But when it does that, it's making another particle and adding it to the nucleus, where all other particles are already occupying the lower energy states. So it's still creating a very high energy proton, right? Or neutron, for that matter.
So when a proton decay, let's take the proton case. When a proton, let's take the neutron case. When a neutron decays into a proton, because there's too many neutrons, above the Fermi level, if you want, right? So it turns into a proton. It has to, did I say that right? Yeah, it turns into a proton. It has to conserve there are certain conservation laws, and we are probably going a little more than I want, but let me just take a moment on this. When a neutron turns into a proton, there's one conservation law called conservation of baryon number. Neutrons and protons are baryons, and so we conserve baryon number. There was one baryon to begin with. There's one baryon to end with. That ends up being basically conservation of quarks as well, if you want. But you create now, you need to do something to conserve charge, right? You started with no charge. You also need to conserve charge. You've created a positive thing, so you have to create a negative thing. And it turns out that the negative thing you create is an electron. Now, an electron is what's called a lepton, and you also need to conserve lepton number as you do baryon number. There were no leptons to start with, and you've now created a lepton in the form of an electron, and so there has to be, it turns out, something else, and that something else is another lepton. It has to be an anti-lepton to conserve lepton number, and the thing you actually end up creating is what's called an anti-electron neutrino. So in the beta decay that I just talked about, a neutron turns into a proton and an electron and an anti-electron neutrino, and that ends up conserving baryon number, charge, and lepton number. And I want to, whenever I say these things, I also feel like I really need to say, does all of this stuff really happening? No, we don't know if it's really happening. What we're saying is this is what really happens in the model that we've created. And that model does a really good job of making predictions. And so we don't care if it's what's really happening, because we can't know what's really happening. All we can know, we can't know what's really happening. All we can know is what's really happening does. So when we measure something, we know, what something has done, and so we can, if our models predict that, we're happy.
That's a wonderful quote, by the way.
What's that?
We cannot know what really happens. We just know what really happens does. I think this is a great quote. I'm writing it down.
I was stumbling all over it. Let me, before you write it down, let me hone it to something better later on. Let's see. Question? Yeah, go ahead, Kirko.
Give me real quick, and I don't want to derail the room either, so you may want to delay it for another day. But like, one of the things that has been really hard to get through my brain, right, is because I have to think about analogies, like from the neutron to the proton and the I think you said electron and anti-electron neutrino that gets created in that process. My brain is saying like that's like you have an apple, you go to a pear, and you make a grape and like a cranberry. But it's like I can get the apple to the pear, but like how on earth would the grape and the cranberry actually be a thing? Because it's like the particles aren't like the same particles. I don't know if it's just like maybe like this has something to do with like the mass giving stuff that's like, okay, well there's just extra energy and it's low enough, so it's just gonna devote that to a different type of fundamental particle. But that's like kind of racking my brain here.
Well, so I don't know if this is going to exactly answer your question, but I'll say it, and then I think I will move on. The neutrino was hypothesized very long time before it was observed, and it was hypothesized on the basis of conservation of energy. It was known that beta decay, in beta decay, electrons came out at arbitrary energies up to some maximum amount. So they're unlike alpha decay, where the particle comes out with a definite energy. Beta particles, these electrons, come out with any energy at all up to some maximum energy. And so you couldn't, if you wanted to believe in conservation of energy, it was kind of difficult because you had some starting nucleus, you had in some configuration, you have it ending in some other configuration, so the energy change of the nucleus is a given. Now, this energy of this electron coming out can be any value, well, how do we conserve energy there? And so Pauli, I think it was Pauli, or maybe it was Fermi. Yeah, one of the two, Fermi, I think, proposed that there had to be some other particle coming out. And he called it the neutrino, meaning a little neutral particle, because he knew, A, it had to be electrically neutral, because we'd already conserved charge. He knew it had to be very small in mass. I forgot to mention that. You end up showing that the electron and the resulting nucleus do have, they got the right amount of mass. You can kind of, or I shouldn't really say it that way, but it seems like mass has already been conserved. It seems like charge is already, well, it's definitely charge has been conserved. So whatever this third particle is, it has to be A, neutral. It has to be very, very massive, maybe massless. We don't know. And number three, it has to be really hard to detect because we don't see it. It doesn't make anything happen. It doesn't interact with our scintillators or things that we use to detect elementary particles. There's no trace of it. So it has to be a particle. Originally the idea was it's a little particle that you can't detect that has no mass and no charge, but it carries energy away. That's pretty unsatisfying. So it was really satisfying when it was finally discovered. And now we detect them all the time, and we know that they're in fact probably the most abundant particle in the universe. And one of the classic things that's said about them is that they can travel through a light year of lead with only kind of about a 50% chance of actually interacting with anything. That's how interaction free a neutrino is. It's penetrated. The reason we don't detect it is because it rarely interacts with anything. And detection always requires some kind of interaction. Okay, I'm gonna move on. Taken probably a little too long already. So one more thing about alpha particles before we get to the alpha decay. This is kind of important. This is really important, actually. When we put an alpha particle together, it's held together by this nuclear glue. And it has what's called a binding energy. The binding energy is how much energy you would have to use to pull the two protons and the two neutrons apart. When you take so that's how much energy it would take to disassemble the alpha particle. It's stuck together with this nuclear strong force glue. The amount of energy, turns out it takes about nearly 30 million electron volts of energy to disassemble an alpha particle. I wrote it down there at the bottom, 28.7 MeV, to disassemble an alpha particle into its parts. Its parts have about 4,000 MeV worth of mass by E equals mc squared, right? Energy and mass are the same thing. They're just different measures of the same thing. The mass of a proton is about 930 million electron volts. The mass of a proton and a neutron are both about 930 million electron volts. Sometimes it's written MeV over c squared just to be dimensionally correct. But people often just kind of take the c squared for granted and just say the mass is this much energy, 930 million electron volts. But when you put them together, we put four of those together, you lose, as you can see, the mass of the resulting thing is about 0.03 daltons. That's what U is. That's basically the mass of a nucleon, plus or minus. Is about 3% of the mass of either a proton or a neutron. You lose that much mass. And that means that if you wanted to get the proton and the neutron back, you'd have to add that much mass. And you add it in the form of the energy that it takes to disassemble it into those parts. So binding energy is a really important thing, as we'll see right away on slide 10. So let's go to slide 10. Finally, tunneling, alpha particles, decay, the thing Shamash asked me a month and a half ago to talk about. In some heavy nuclei, and not all, but in some heavy nuclei, two protons and two neutrons can effectively form an alpha particle within the nucleus. And what that does is when you form that alpha particle, you end up losing mass. I mean, the whole nucleon, if you really did think you'd formed this alpha particle, you'd have less mass. Well, the only way you can have more mass is to add energy, and that energy is in the form of kind of lifting that alpha particle out of the potential well that all of those nucleons that it's made out of lives in. So it lives down there below. It lives down there in the energies below zero, the parts that can't exist outside the nucleus, and it raises it up above them by that binding energy. So now you end up with an alpha particle, which itself has less mass, but now has so much energy that it's now lifted into the region where it has enough energy to actually exist outside of the nucleus. But it can't get outside the nucleus because it doesn't have enough energy to escape the potential well it's in classically, right? And so we're just back to the very beginning here. We know it's going to get out because we know about tunneling, and all that's left for us to do is to do a detailed calculation of what that tunneling is, which we're not going to do, but I'm going to sketch in the last few slides. So the slide at the left on slide 10 there, I mean the figure on the left on slide 10, shows you that binding energy that's lifting the alpha particle out of the continuum of nuclear energy levels up to that level where it can now exist outside the potential well if it can get there. And then that little RB that's shown there is how far it has to go to get to the allowed region through that forbidden region created by the Coulomb, or electrostatic, if you want, potential. So that's what that diagram is showing. And then the diagram on the right, both of these, by the way, link to the pages that they're from. And that one on the right kind of shows you now with a well, with a symmetric well. Right? The one on the right, once again, refers to a symmetric well, whereas the one on the left only has that kind of half well, starting from the center of the nucleus out to its radius. The one on the the one on the right shows you the symmetric well, so the full diameter of the nucleus, if you want. Schematically, it shows the big wave function in the well, decaying in the forbidden region to a smaller wave function outside the well. And that's what we're going to be looking at. You don't have to worry about reading most of those things, but that picture is what we're going to look at in the next couple of slides. Let me just stop there for a second, too. Any comments, questions? So what we're going to do is we're going to we're going to now be doing this for an energy eigenfunction. I'm going to look at, because we actually know what the energy of these alpha particles, we can take, for instance, we're going to look at polonium-212. Is that what we're looking at here? No, sorry. I'm getting ahead of myself. Let's just go to slide 11 here for a moment. So a quick kind of a mathematical tour of barrier penetration. We've never actually done this mathematically because it's just too hard. Some of you can do it if you want. You can click on the picture there. That'll take you to the page where the actual calculation is done. Links to other pages that do the calculation even more carefully. But trust me, you don't want to do this. It's ugly. It's ugly math. So all I want to do is kind of sketch basically what we do. When we talk about barrier penetration, try to get numbers for it. This is what we do. First of all, this is back to the simple case of a rectangular barrier. Some particle with energy less than U naught, the height of the barrier. And what we do is we say, okay, I want to have particles coming in from the right. I know that those particles are going to reflect off of the front side of that barrier. They're going to decay. The particle's wave function is going to decay in the forbidden region, but they're also going to reflect off of the down step on the other side. And then I'm going to get a wave traveling off to the right in the other region. So I'm just going to hypothesize here that the incident wave function is going to be, and this is kind of in wordy math, it's going to be a sine wave to the right plus a sine wave to the left, which reflects the which is corresponding to the reflected wave. Notice I put a coefficient r in front of the sine wave to the left because I want to allow for the fact that the reflected sine wave is going to be slightly lower in amplitude than the incident wave, because some of that wave is going to be transmitted into the forbidden region. So notice I didn't put a coefficient in front of sine wave to the right because I get to just let one of these things be 1. I'm just going to let 1 be the amplitude of the sine wave to the right. And now I can guarantee you that r will be a number something less than 1. Probably not very much less than 1, frankly, but it's going to be less than 1. And it's going to be complex, too, so it's worse than that. It's going to be a complex number, which is why we don't want to really do this. Within the barrier, the wave function is going to be a sum of a decaying exponential and a growing exponential. I can just really say that. I just know those are the only two things that are allowed there. The rate at which they decay or grow just depends on the difference between U0 and E. And so I'm just going to put some arbitrary constant a times a decaying exponential plus some arbitrary constant b times a growing exponential. That's the wave function within the barrier. And then on the exit side, I'm just going to have some coefficient that I'm calling t to the 1/2. Why do I do that? Well, we'll get to that. But it's just a constant. It's just a number. T to the 1/2 is just a number. And I'm going to multiply that times a sine wave to the right. Because over on the right, I won't have anything traveling to the left. There's no reason for anything to be traveling to the left because there's nothing for that rightward traveling wave to reflect off of. So I propose that the wave function for this thing will correspond, for this energy, will correspond to this. And now what I do is I write 4 equations which say that the incident wave function the value of the incident wave function has to equal the value of the wave function in the barrier at the left side of the barrier. And the same kind of thing happens at the right side. The wave function in the barrier has to equal the wave function on the exiting side, the exiting part of the wave function at the at the right side of the barrier. That just means that the wave function has to be what we call a continuous function. You can't just have an arbitrary change in value at any point. And there's one other condition that that wave functions have to satisfy is not only do they have to be so-called continuous, but they have to have a continuous slope. So if the wave function is sloping in some way at one barrier, it has to slope in that same way on the other side of the barrier. If you know what that means taking derivatives of the equations, setting them, derivatives of the expressions, setting those derivatives equal at the two sides. It ends up giving you 4 equations. Without belaboring the point, I end up getting 4 equations, and notice I have 4 unknowns. I have the coefficient r, the coefficient a, the coefficient b, and the coefficient t1/2. So I have 4 equations in 4 unknowns. You may remember from math that when you have 4 equations and 4 unknowns, you can solve for the 4 unknowns. The only one I care about is that one t to the 1/2. And so I solve for it. And what I find is that it is e to the minus alpha d, so that t itself is e to the minus 2 alpha d. And I call it the transmission coefficient because what it really is it's the ratio of the amplitude of the wave traveling to the right. The ratio of the exiting wave traveling to the right, its amplitude, to the amplitude of the incident sine wave traveling to the right. That ratio of amplitudes tells me the relative probabilities of being on one side or the other. But we remember maybe that the probability is the square of those things. So what I have to do is I have to take the t1/2, divide it by the amplitude of the incident wave, which was 1. We chose it to be 1, and then square it. I'm saying more math than I even want to here. The net result is that we get a transmission coefficient, which is approximately equal to, this isn't exact, but it's approximately equal to e to the minus 2 alpha d, where alpha is that thing, the square root of twice the mass of the particle times the difference in energy between the top of the barrier and the energy of the particle, square root of that thing, divided by Planck's constant. It's that simple, even though the process of getting there is nothing like simple, and we've made all sorts of approximations, et cetera. But the takeaway from this is that for instance, for a particular example of U naught being 26.4 MeV, the energy of the alpha particle being 8.78 MeV, and the mass of the particle being 4 Daltons, which is the mass of an alpha particle, we get that transmission value. And I only point that out to say that these numbers reflect the values for what's called polonium-212, I think we're going to talk about in the next slide. And that transmission coefficient is really small. Right, the amplitude of the wave on the far side is vastly less than the amplitude of the wave coming in. It's less by a factor of 10 to the 14th, so that when I square it, I get less by a factor of 10 to the 28th, 10 to the 29th, like this. Very, very little gets through that barrier. Okay. Wow. This is going on for a while here. I recognize that too. Congratulations, everybody hanging out. Okay.
What are we talking about? We're having so much fun.
Okay. Well, good. I hope so. I hope you are anyway. So, all right. So why did I use those values? Well, because what we really want to do is just pay homage to George Gamow, who 2 years after Schrodinger proposed this model for alpha decay. He proposed exactly what we're talking about, that the alpha particles formed within the nucleus, the energy released essentially in that forming raises it up into a region where it could exist on the outside, and then it tunnels through the barrier in the way that we've talked about. And those numbers that I gave you are applicable here. So what's really happening is on page 12 is the barrier. The actual barrier is that Coulomb barrier in light gray, that kind of downward flowing 1 over R shaped potential barrier. What you could do to kind of get a handle on this is say, well, let's just replace that actual barrier with a rectangular barrier that has the same height and the same height as the maximum and the same width. So it turns out to be about 19 femtometers in width and about, what is that? About 15, 16, what did I say on the previous page? Yeah, well, okay, so about 18, I guess, MeV above the energy of the particle itself. And then you get that dark gray barrier. So let's replace the actual barrier, the light gray, with that dark gray barrier. Now we know that's probably going to underestimate the amount that gets through, because this is now a taller, it's no wider than the actual barrier, but it's taller. And that means that the wave function will decay much more quickly in there. So this will probably give me an underestimate. But we want to try to model polonium-212, which emits an 8.78 million electron volt alpha particle with a half-life of 0.3 microseconds. Polonium-212 is an element that you don't see in nature because it decays away with a half-life of less than a millionth of a second. We create polonium-212 in nuclear explosions, fission kinds of events, some of it is, and it's intensely radioactive because basically anything you produce immediately produces an alpha particle and decays to something else in the process. But we're trying to kind of work out that half-life thing. So what we do is we first of all say, well, let's see what the transmission coefficient is. we get transmission coefficient, as I said on the previous page, actually, I didn't say quite that. I guess I used slightly different numbers. The transmission, when you put in those values for the height of the barrier and the width of the barrier, and you use a rectangular barrier, you get a transmission coefficient of 4 times 10 to the minus 29th, a probability of 4 times 10 to the minus 29th that it gets through. When a particle bangs up against that barrier, it gets through with a probability of 4 times 10 to the minus 29th. That's almost nothing. To get the half-life, we basically need to know how many times per second the alpha particle will bang up against that barrier. And we do that by assuming that it's basically knocking around in the nucleus, traveling at the speed that is reflected by its energy, and that means that we basically we calculate the time it takes to go across the nucleus and bang up against that wall as the diameter of the nucleus divided by its speed, 2 times the radius divided by its speed. Well, the radius we know from other things to be about 9 femtometers for a polonium-212 nucleus. And the speed is going to be basically determined from its kinetic energy. That's what that square root of 2e over m is. And it's fast, by the way. It's a little less than 10% of the speed of light. That alpha particle's banging around at about 10% of the speed of light, which is largely non-relativistic. A particle going that fast isn't very relativistic. Has to go closer to maybe half or a third or a fifth of the speed of light before you start really getting relativistic effects happening. So it takes only 10 to the minus 21st seconds to cross the nucleus. And that means that it's going to bang up against the wall about 10 to the 21st times per second. So it bangs up against the wall 10 to the 21st times per second. Every time it bangs at the wall, it has a 10 to the minus 29th probability of getting through. I say 10 to the minus 29th rather than 4 because I'm being very loose with numbers here. If you just take those exponents, that's about all we care about. You get 10 to the 21st whacks at it. Every time it hits it, it has about a 10 to the minus 29th probability of getting through. That means that the probability of getting through after a second is still only 10 to the minus 8th. So given this barrier that we've chosen, given the calculation of the transmission coefficient from what we did before, we calculate a probability that it gets through that barrier in 1 second of 4 times 10 to the minus 8th. And it's a few steps from there, which I won't go through, to show that the half-life of this part, if you believe this is what's going on, then you'd have to wait about 6 months for that probability to be enough to say, okay, it's about 50% likely to have gotten through by now. About 50% of the probability wave that we saw in the first couple of slides will have now decayed through that barrier over into the outside. It takes 6 months. Now remember, this thing we're modeling has a half-life of 0.3 microseconds. So this is a really, really bad calculation we just did. We are off by a factor of 10 trillion on the half-life. And as I say, it shouldn't be hard to see why shouldn't be so hard to see why we got the wrong answer. Especially shouldn't be hard to see why we are on the high side of the actual value. But it may be a little bit surprising to realize that difference is due to the fact that we used a rectangular barrier, which is, the same width, but much higher in general than the actual barrier. Using that rectangular barrier rather than the actual barrier threw us off by a factor of 10 trillion. So what Gamma did at this point is he said, okay, I know what the transmission is through a rectangular barrier is. Let's just make a bunch of little rectangular barriers, each of which I know the transmission for, and just figure out what happens if I put them all together. So on slide 13, you'll see figure kind of showing you that. Let's take the actual barrier and now approximate it by 5 rectangular barriers, which kind of have, as best as can, the shape of the actual barrier. And when you do that and you calculate the transmission coefficient for each one of those, multiply them together essentially to find the overall transmission, and then carry through the calculation, you get a value for the half-life of 0.25 microseconds. Remember that the observed value is 0.3 microseconds. And so this value that we get in this particular case using 5 barriers, this is what you get using 5 barriers, is embarrassingly good. It's embarrassingly good because there's no way it should be anywhere as close to the actual value as we got. So somehow we got very lucky. And I don't even know how it may be that in the time since then, people have discovered that if you do the 5 rectangle analysis, you just happen to get a really, really good value. And so that's what's often shown. But it should be understood that that's an embarrassingly good agreement. Getting that good an agreement on something that is so exquisitely sensitive to barrier height and width can't possibly be anything other than a really fortunate accident.
Random question real quick.
Yeah, go ahead.
So like, is it possible, because like when you look at the first one, it's just the one barrier, like versus like the little curve, there's like a whole gap of space on the outside of the curve where the energy barrier still is. Then when you make the 5 barriers, like that gap decreases. Is that like any correlation there? I don't know if that makes sense.
I'm not sure I understand your question, Kirko. Try again.
So like on slide 12, I'm just looking at the graphs on the right. So the darker gray box is like the energy barrier, correct?
Mm-hmm.
And then on the bottom slide, the energy barriers are more fitted to that slope.
Right.
So is that why? Because like,
oh, absolutely. That's definitely why. The embarrassing part is that it does such a good job, because there's no way it should be. When you realize that we were off by a factor of 10 trillion when we did it with the first one, the fact that we're now off by 20% is just, using still square barriers. And by the way, it's worse than that, because we're also assuming that on the far side of the barrier, there's the potential goes back down to 0. That's the way we get those transmissions. So all of that gray area to the right of the dark gray goes away in both of these models that we're talking about. And that's also not true. So there's all sorts of things wrong with it. I don't know. Does that help at all? Anyway, but that is what we're looking at. And so I just want to finish. I'm really done, except for just the last slide, which I think makes a really important point. If you think about carefully, when you do this carefully, you do get good results. So you can make calculations of these things. These are difficult calculations. They're probably never to more than 1 or 2 significant figures, even when they're done very carefully. But one thing that becomes really clear is that the most important thing is the energy of the alpha. And on page 14, I'm trying to show that all of these nuclei basically have the same potential function. They're all big nuclei. They're all essentially the same size within, 10, 20, 30% at least. They all have essentially the same kind of peak energy there at the far end of the energy well. And so none of that stuff changes very much. The only thing that really determines the effective size of the barrier is the energy of the alpha particle. And so on the right side of that page, you see how incredibly much smaller the barrier is for an 8 MeV particle than it is for a 4 MeV particle. It's narrower, it's not as high. Above the 8 MeV, you just go up to the peak there and then you come down. It's narrower, it's not as high. For a 4 MeV particle, it's way wider, and way higher. And the transmission coefficient depends with exponential dependence on how high and wide it is, that alpha parameter, alpha D parameter that we saw a couple slides ago. And so you should expect you should expect nuclei that emit high energy alpha particles to have shorter half-lives, just because if it's a high energy alpha particle, it's going to be a small barrier and it's going to get through in much shorter order than if it's a low energy. And it's kind of remarkable to see just how true that is. The final graph on the right there shows half-life of isotopes versus the energy of the alpha particle that those isotopes emit. And what you'll see is that for alpha particles with an energy of about 4 MeV, 4 million electron volts, they're associated with half-lives on the order of the age of the universe. Things like U-235, I think most radioactive elements that we find naturally have half-lives of billions of years, because if they didn't, they wouldn't be here. They kind of have to have a half-life of 1 billion years or they'd be long gone. And in fact, the lowest energy alpha particles, the lowest energy alpha particles we see from these things are like 4 MeV, and those are associated with isotopes that have half-lives that are approximately the age of the universe. If I just double that energy to 8 MeV, we now are talking about alpha particles associated with isotopes that have half-lives measured in millionths of seconds. So just doubling the energy of the alpha particle reduces the half-life by something like 25 orders of magnitude, 25 factors of 10. That's how strong the dependence on energy is. And you see there that there is. I mean, the nice thing about that graph there is it just shows that it really is, the half-life really is very strongly correlated with the energy of the alpha particle, as you would expect from this tunneling model. So that's the end. I'm done. Slide 15, the end of the quantum series. I'm done. Sorry, I went on a kind of a long time today. But we can continue if there's more discussion to be had. Anybody, raise your hand if you want. Kirko, go ahead.
So when it comes, so if there's such a dependence on the energy of the alpha particle, if there's more energy in the atom itself, would that put more energy in the alpha particle? So like if you were to move it real fast, like the atom itself.
Yeah, so of course the motion of the atom itself, and really let's be really clear here. These are nuclear processes. The atom itself is completely irrelevant. You might think that the electrons around the nucleus would kind of come into play somehow, but the energies involved in the electron interactions are 1 million times smaller than the energies involved within the nucleus itself. The nucleus doesn't give a damn about the electrons. The electrons are all about the nucleus and each other, but especially the nucleus. But the nucleus doesn't care if it's got electrons around it or not. So you could just as well just think about the bare nucleus, but you might as well, if you want to talk about the atom, that's fine. Now, it's not going to make any difference if you shoot that atom at 50% of the speed of light. Because there's no such thing as absolute velocity. That atom is just as much a non-moving atom as any other atom is. The only reason you say it's moving is because you see it moving, not because, quote, it is moving. No such thing as absolute velocity. So that has no effect on the process whatsoever. A nucleus will decay based on its own properties. And because those properties are quantum properties and they're quantized, they come only in certain forms. And that's why you see essentially a polonium-212 different. So radioactive nuclei will have different decay modes in general, but there are some that only decay. Well, yeah, for any given isotope, there are only a few kinds of decay modes, and there are certain. I don't know if polonium-212 has another decay mode. It may be that the only thing it can do, and that it does do, is decay by alpha decay immediately. Basically, I don't know that. I should look that up and see. When a polonium-212 atom decays by alpha decay, it becomes, because it's lost 2 protons and 2 neutrons, it becomes a different element, right? This is nuclear transmutation into a different element. It becomes whatever element is 2 atomic numbers down in the periodic table. Somebody could look that up for me. I don't know what that is. And it becomes and it becomes that element with also 2 fewer neutrons. So it becomes an isotope with an atomic mass of 208, and then whatever is 2 numbers down from polonium, and that's what it does. And that isotope itself may be radioactive. So we have these radioactive series that I think I talked about in a previous bite of physics. I talked about radioactive series, of which there are 3 that naturally occur, because this decays to that, which then decays to this. And they always do that because, you can't just like nudge the energy, right? If it's a nucleus of this, it is a nucleus of that, and that's all that matters. And it will decay the way that nucleus decays, because these things can only be in quantum states, discrete quantum states with definite energies.
So just to like round out this question, because I think it's pretty much answered, but just so I'm sure, since there's no dependence on the actual atom, it's all nuclear energies. That means that the only thing that would determine this ability would be the actual like constitution of the nucleus, like how many protons, how many neutrons.
Right. Now, there is this thing, of course, that I talked about, excited states of a nucleus. So you can have this many protons and this many neutrons, but maybe one of the protons is not in as low an energy state as it could be. And then typically what happens is it will de-excite into that lower energy level and emit a gamma ray. So gamma decay is kind of a different thing. Both beta decay and alpha decay changes the chemical element. The chemical element itself changes. In gamma decay, you don't change the number of protons or neutrons. You're just having a proton or a neutron jump into a lower energy state and emit a photon. So gamma decay is a little bit different. We really talk about it in terms of excited states of isotopes rather than the kinds of decays that change the actual chemical element. Yeah. Okay. Good. Thanks. I can't believe you guys all sat through this. I mean, it's a hardy crew here. That was tough sledding.
Thank you so very much. Okay, I'm gonna leave the emotional monologue to the very end. There's another question in chat.
Okay.
From the Methyl. She asks, how is it that quantum tunneling for alpha decay particles differ from when it works with electron tunneling, let's say in semiconductors, when they become very, very small?
When they be you mean
when the semiconductor,
right.
Because there's this rule, if it's under 3 micro or nanometers or something, it doesn't work anymore or something like that.
Yeah, well, I don't know much about the solid state physics of semiconductors, especially with these incredible chips that we produce now. But the fundamental physics is the same thing, and the idea is that you can affect kind of radical controls on the flow of current without having to do much, right? You increase the barrier a little bit, you can basically effectively shut off. So transistors were, initially they were used kind of as a replacement for tubes. They were used in their so-called linear regime, where you would use the control of voltage, like a tube does, a small amount of current that controls a large flow of current that you use to send current to your speakers of your stereo system, etc. But they also, transistors are easily turned into kind of binary off-on things by just using that control voltage in a saturated mode. As I say, the kinds of things I'm saying now just reflect how completely ignorant I am about solid state physics. But even to refer to them as transistors is kind of a silly thing. A transistor is kind of your simplest thing next to maybe a diode of a barrier across which electrons tunnel. Now, I don't know. I probably haven't answered your question at all. I think the basic answer is it doesn't differ. It's the same. It's the same quantum physics, just applied in a kind of a different scale to a different system.
So one final question. We said that the major determination of the decay happening or not is not exactly the depth, let's say, between quotations of the atomic well, but the energy of the alpha particle. So what does really determine the energy of the alpha particle?
Right. I was afraid somebody would ask that question. I was kind of asking myself that question earlier today. And I'm not entirely sure how that works. When that whole business of lifting it out of the well, I mean, if you look at the energy, the binding energy of the alpha particle of 28 MeV, that suggests that you ought to be lifting it somehow by 28 MeV out of the well. And it may be that that's what's happening. I don't know enough about the nuclear physics to know if like the top energies there are 20 MeV below zero. If they were, then lifting it by 28 MeV would give you maybe an 8 MeV alpha particle above zero. But I just don't know. I'm completely talking out of my ass here because I just don't know enough nuclear physics. But it's a really good question. I don't know what it is. I imagine it has to do with something about that Fermi energy, but there's probably other stuff going on too. Let's see. So what else? We were talking about kind of the Pauli exclusion thing before. I don't really have much more to say about that, but one of the things that governs all these particle physics, nuclear physics kinds of things is identifying so-called quantum numbers, and in particle physics in particular, there's all these exotic quantum numbers, iso, spin, and parity, and all sorts of things, that all of which have to be conserved. And the game of particle physics, in some sense, is identifying quantum numbers, demanding that they be conserved, and then essentially saying, okay, if I can come up with a set of things on one side of an equation and a set of things on the other side of the equation that conserve all quantum numbers, then that's a reaction, in some sense, that has to happen. If any reaction that conserves all of the necessarily conserved quantum numbers is a reaction or a decay, if you want, or whatever, an interaction, a process that must happen, because there's nothing preventing it. If it doesn't happen, maybe you've discovered some new quantum number that is the thing not being conserved that's preventing it from happening. I don't know how much people work that way, but I think that kind of thing happens from time to time as well.
The way it was explained to me, and maybe you can lay some light on it, is that when you have two particles with exactly the same characteristics, what ends up happening is the waves that represent these particles, well, that's already a mess up. There are no particles, there are waves. But, their waves will meet in a destructive way, which leads to a probability zero everywhere.
Yeah.
And so you got to move one of them to another state of spin so that they can coexist.
Yeah, that's right. It has to do with what are called symmetric and anti-symmetric wave functions. And fermions have anti-symmetric wave functions, which means something like that. I can't remember exactly how it goes, but you're putting your finger exactly on the thing. It has to do with the mathematics of anti-symmetric and symmetric functions and what happens when you put them together. Bosons. So one of the things about bosons, like helium nuclei, for instance, helium nuclei have zero spin, I believe. Maybe excited states can have. Anyway, they have integer spin primarily because they have an even number of fermions making them up, which can only add up to an integer total spin. And because helium nuclei are bosons, if you talk about collections of helium nuclei, you can put them all in, if you think of them as particles, which you're always able to do, right? We can think of protons and neutrons as particles, even though they're made of quarks. We can think of helium nuclei as particles, even though they're made of neutrons and protons. And you can put a bunch of helium nuclei if they're in a well of some form, you can put them into the same quantum state. Because they are bosons, they're not fermions, they have symmetric wave functions, and that's what's called Bose-Einstein condensation. Some fellow, I think Colorado, Cornell, somebody got the Nobel Prize for illustrating the first Bose-Einstein condensate, 15 years ago, 20 years ago, something like that. Okay, I think we have somebody who actually knows something about this. Ahmad, if you'd like, I invite you to come on stage and correct the things I've said that are wrong, and maybe go further. Let me invite you on stage if you'd like. Don't feel compelled, but I'm always interested in hearing where I'm wrong. And boy, in this stuff, I'm more likely to be wrong than in most. Anyway, Ahmad says, even though this is general. Oh, are you there? There you are, Ahmad. Hey, welcome. Nice to meet you. Would you like to introduce yourself and say a few words about this?
Yeah, sure. I'm recent graduate from NMC program in theoretical physics, particle physics in general.
Excellent.
I mean, I wouldn't say you've said wrong things. I was just saying that there are certain reactions within the standard model that take place even though, for example, certain quantum number is not conserved, like strangeness, for example, in weak force interactions.
And is that an indication? I mean, so you, because I understand the whole thing about, of course, strangeness was a very puzzling thing. 40 years ago, 50 years ago, which we've kind of come to terms with since. But that doesn't. Is it really just accepted that these are literal non-conservations of quantum numbers, or are they hinting at some other, because it's like the CPT thing, that charge conservation, parity, time reversal thing. I think they thought that you had to have, that each one of them was conserved, but it isn't. I'm sorry, my question isn't very good, but I'm just wondering if it's really the fact that we just accept that these quantum numbers are not conserved, or if it's hinting at something that we don't quite know yet.
Yeah. So regarding the CPT, and when it's combined, then we know that it's conserved. But then problems arise when we consider, for example, one of them or a couple of them, and for example, weak nuclear reactions where the W boson is being exchanged, so not the Z boson. And also about strangeness, then it would be an indication of a weak interaction taking place, not electromagnetic or strong interaction,
right?
Because the strangeness is being conserved in the strong and the electromagnetic forces.
Yeah, right. Yeah, thanks. Yeah. Well, anyway, welcome. Thank you for coming, and I hope you'll come in the future, even when I'm talking about things that I actually may know a little more than I do about this one. I really appreciate having you here because I'm out on thinner ice on this topic than I am on most things. Hermes, welcome to the stage. Did you have a question?
Yeah, guys, it's Friday, and quantum entanglement is on the minds of everyone. I love that. So thank you for allowing me on your stage. This is awesome. I'm going to look at that document there at the top.
Good. Yeah, let's see. So any other things? Anybody in the audience? Let's see. Shane says, if relative level of radioactive saturation Is relative level maybe of radioactive saturation dependent on depth of regolith on the moon or Mars? If it's relevant to the topic, what can be expected to be observed at various depths? Oh boy, now we're really, I'm not even going to attempt an answer to this one. Sorry, Shane. Yeah, no, I don't know. I don't know how to even approach that one. Let's see.
I'm not sure if he's talking about the depth as in a metaphor to the depth of the energy levels, like when we talk about on a graph, or are you talking about geographical depth of an actual pit?
It sounds to me, correct me if I'm wrong, but it sounds to me like he might be talking about cosmic ray excitation of radioactive isotopes. I have my goddaughter goes to Antarctica and makes measurements on rocks. She picks up rocks at the sides of glaciers and determines how long those rocks have been uncovered by ice in an attempt to measure glacial retreat by looking at the excitation of what is it? Beryllium, some isotope of beryllium. So she's basically it gets activated by the impinging of cosmic rays at a kind of a known rate, and she takes them home, crushes these rocks, gets the levels, does kind of it's basically like a reverse carbon dating or something. How long this isotope has been being activated tells you how long the rock has been exposed without ice over it. And it sounds like it might be talking about that kind of thing. The cosmic rays may be getting cut off with depth in the regolith. How long does radioactivity store? Oh, well, as far as if the question has to do, actually he says ding ding, so I guess I was in the right ballpark. But if the question really is, Shane, about, and you're welcome on stage, by the way, if you want to come up and explore this further. But if you're talking about how storing radioactivity, how long it stores, that, as I was saying before, the nucleus doesn't care where it is, doesn't care what its surroundings is. The nucleus makes its own environment. You can heat these nuclei all you want. You can do whatever you want to them. I think it's fair to say, maybe Ahmad can correct me, I don't think there's any way to heat a nucleus and change this. Maybe there would be effectively, but probably would require tearing it apart. It makes its own energy environment, and its energy environment is what determines its energy levels, the states of the isotope and the decay modes and the energies of the decay products, et cetera. You're certainly not going to change that by burying it or by anything you do to it other than the fact that you have it to begin with.
Hi, John.
Hi, Sam. How are you doing? Good to see you.
Hello.
Doing okay. The last couple of months, I've lost the ability to plan and to actually, if I do plan, carry it out. It's been really weird. So
is this? Yeah, I know you've.
Yeah.
I know you've had some health problems. Hope those are getting better.
Yeah. And Debbie and I have been involved with kind of a personal project that for the past month or so that basically takes a lot of oxygen out of the room.
Well, I think anything that gets you off Clubhouse is probably a good thing, right?
Yeah, I guess. Well, I miss my chemistry and pharma rooms.
Yeah.
My own rooms. I miss them. So I kind of want to come back.
Well, I just want you to know that they're going fine.
Oh, thank you very much. You've started giving the
oh man, wouldn't that be something? Talking about getting out over my skis. Watch me do some DNA rooms.
Yeah, just as good as my doing physics rooms.
Yeah,
so
great.
I just wanted to kind of agree with you that nuclear decay is completely independent of environmental conditions, and this is why we have nuclear clocks, right? So
yeah.
So the because the half-life it remains unaffected. What gets affected is how much radiation gets out. That is, right? I mean, if you have a lot of lead around
Right.
it, then radiation doesn't get out. But
Yeah, right. Yeah, well, listen, we've gone on longer than usual here today. I think I'm going to head toward shutting it down, but I'll invite everybody to dig deep into their brains and come up on stage if you haven't actually. It's not too late to come up, and if you do have a question or comment. Let's see. Let me look here again. I see lots of stuff going on in chat. Bert, good to see you. Sorry you can't talk. Glad you're back. Shane. Dimethyl. I assume after going in a couple meters or so deep, radioactivity will stabilize since cosmic rays. So I guess, I mean, there's that thing, of course, is that you can have, if you're talking about activation of different kinds of isotopes, exciting isotopes with cosmic rays, there'll be a point, of course, where the shielding, and that's really what my goddaughter does, is she looks at things which don't get activated when they're covered with ice, but do when they're not, and the amount of activation tells you how long they've been uncovered by the ice. So it's kind of fun, great research for doing kind of long-term 10,000 plus year retreat of glaciers in Antarctica. And thanks, Ahmad, for your kind words. You're always welcome back here. Appreciate having people who know what they're talking about around. All right, I think I am going to go. Thanks everybody for coming. Thanks especially for sticking around.
Thank you.
Yeah, and next week.
All thanks to you.
I don't know exactly what we'll do next week, but I'll figure it out and
we can do whatever you want.
Yeah.
I just want to say at the very end, thank you so very much for everything you're doing, and thank you specifically for this series. I know how much research it requires, and thank you for the wonderful slides. For those of you who are here for the first time, this has been a 5-week series on quantum mechanics. You will find all 5 episodes of this on the YouTube. I'm going to paste the link for the scientific discourse on YouTube in the chat again. Give us a follow. You will also find playlists for the other series we're doing, which is about mathematics and philosophy. This happens every Wednesday, same time, 17:30 GMT. Our founding member, Sam, is also here after a long vacation. I don't know, can we call it vacation? He's been away. So once he restarts his chemistry and his biology series, they will hopefully be up there as well. So give us a follow and follow our founding members and the house for more.
Yeah, thanks, Shamash. And I see Shane has joined us here. Shane, did you want to make a comment or have a question before we go?
Well, I'll just say thanks. And what is, I guess, from my perspective, I was looking at as from the environment perspective of it being exposed to radiation and then that accruing over time rather than it like the element itself.
Right.
So that was helpful. Thank you.
Right. Yeah. No, that sounds like I mean, I don't know. Do you do some work like that? It sounds like you must know something about it.
Environmental. So like architecture, but I've tried applying environmental tools to extreme environments where that curiosity has been explored.
Yeah, no, I mean, it really sounds, the more I think about it, everything you said is exactly the kind of thing that my goddaughter does in Antarctica with her research. So that's pretty interesting. All right, everybody, thanks a lot for coming. And we will... let's see what we play out with here. Maybe we'll play out with this guy. Okay. All right. See you next week.